Our today's session and tomorrow's session, it will be basically the exercise on columns. In first session, that is the today's session, we will be having an exercise of acid gas treatment plant in Aspen HYSYS, like how to simulate acid gas treatment plant in Aspen HYSYS. And tomorrow, you will be we will be going through how to simulate an NGL fractionation train in Aspen HYSYS. These are basically the exercises on use of different columns. It's my kind request that uh, don't miss any of the parts of today's and tomorrow's session. Why I'm saying it like this, because in your certification exam, I've seen till now there are questions in the lab part, because lab part will be having only one simulation. That entire simulation you have to do, and based on that, different question will be asked. So till now in the lab part, there are questions on NGL fractionation train, like 90% of the times. So if you do that thing, and if you attain the different exercises on columns that we will be covering in today's and tomorrow's session, you will be like more confident, or your chances for passing in that lab part of the certification examination will be increasing. That's why it's my kind request to don't miss any of the part of today's session as well as the tomorrow's session. Also, we will be having one more session on compressor modeling. So that part will also be there in some of the Aspen HYSYS certification examinations. So we just request don't miss that part as well. So let's start with today's session. What is this acid gas treatment? Is exactly acid gas treatment. It is also known as a gas sweetening process. It is the process of removal of acid gases like hydrogen sulfide and carbon dioxide from a natural gas stream. So basically, it's a process of removing the acidic gases. That's why the process is called as gas sweetening, because we are removing these acidic gases from the natural gas stream. This is typically achieved using an amine absorption, which involves using an aqueous solution of amines to capture the acid gases. So these acid gases along this natural gas stream along with the acid gases is passed through an amine solution using an absorber, which captures the acid gases, and the treated gases is known as sweetened gas or the sweet gas, because it is having less acid gas content, or almost it is having no acid gas content. That's why the treated gas or the gas which is coming as a product of this process, it is called as a sweetened gas or sweet gas. So what this process exactly involves? It involves the three stages. First one is the obviously acid gas removal, then solvent regeneration, and acid gas disposal or utilization. So we will just see these processes one by one. A typical acid gas removal process consists of three steps. First one is acid gas removal. In this process, what is done is a liquid solvent, which is typically an amine solution, is counter currently contacted with an acid gas stream. That means natural gas containing acid gases stream into an absorption tower. The amine solution, it selectively absorbs H2S and CO2 from the stream. It takes out these two gases and passes the natural gas stream without these gases for the further processing. Then comes the solvent regeneration. It means that the amine solution, which is loaded with acid gases, is heated in a regenerator, which breaks the bond between amines and the acid gases, releasing acid gases as a concentrated stream. The amine solution is then regenerated and recycled back to the absorber column from the reuse. This regeneration process, it is generally carried out into a distillation column. In that distillation column, the feed is preheated for some temperature. It is then passed to the distillation column. From that distillation column, the acid gases will be removed. How it is done? By breaking the bond between the amines and the acid gases. And the liquid amine, it can be recycled into the absorber column for reuse. Then what is done with those acid gases which are removed? These gases are either disposed through incineration process, or they can be further used for applications such as sulfur recovery. The concentrated acid gases can be incinerated to convert them into harmless byproducts depending on the application and the concentration. The acid gases can be further processed and utilized for the purposes like sulfur recovery process. So what is the purpose of this acid gas treatment? Why this acid gas treatment is done? The first and very important purpose of this acid gas treatment is the safety aspect. As we all know that H2S, that is the hydrogen sulfide, it is highly toxic and flammable gas. It can be proved to be dangerous, or we can call it as deadly when it is exposed in high concentration. So it also forms some of the corrosive acids like H2SO4 when it comes in contact with water, and it can be harmful to other equipments as well by causing corrosion in them. So considering these aspects, this gas should be removed from the natural gas phase. Second aspect is, or the second purpose is environment protection. CO2, as you all know that it's a greenhouse gas, and removing it from the natural gas, it will help to mitigate the climate change. So CO2 removal will also be important. Product quality, industrial processes and the end users which are using those natural gas streams, they have stringent norms regarding the purity of those gas streams. That's why they do not want the contaminations like H2S and CO2 in that. So for that reason as well, this acid gas treatment is performed. And the last part is improved process efficiency. Acid gases can contaminate the natural gas streams by making it not suitable to carry out through a pipeline, because it will ultimately form some acid like things, and it will be resulting into corrosion of the pipeline. Also, if there are some downstream applications, it will cause, or it will affect those downstream applications as well. Removing, removing the acid gases from the natural gas stream, it will increase the process efficiency by avoiding the phenomena like corrosion of pipelines and other equipment. So we can achieve the improved process efficiency just by removing the acid gases from this natural gas stream. So before going for this plant exercise, let me take you through a quick video that explains what this process of acid gas treatment actually works, and how the you will get an overview like what we have seen these three stages: acid gas removal, solvent regeneration, and acid gas disposal. That part is not shown in that video, but these two processes and the recycle process is shown in that video. So let's have a quick overview of.
Amine sweetening is an important process in the oil and gas industry. With it, natural gas is stripped of its hydrogen sulfide and carbon dioxide, preparing the gas for sale or further processing. In this video, we're going to have a look at some of the inner workings of amine sweetening. In particular, we are going to have a look at how the absorption and stripping system works. The typical amine sweetening process contains two steps: absorption, where the amines absorb the H2S and CO2 from the sour gas, and stripping, where the H2S and CO2 are stripped from the amines and discharged. Absorption begins with the inlet separator. Here, any solids or liquids are removed from the sour gas using baffles and mist extractors. The gas then makes its way into the contactor column. Here, comes into contact with the amines, and the H2S and CO2 is absorbed from the gas. These columns are often divided by trays. These trays contain bubble caps, which allows the gas to rise through them without the amine solution seeping through. The trays also contain weirs and downcomers that help control the downward flow of the liquid amines. Gas enters the column from the bottom. As it rises, it comes into contact with the liquid amines on the bottom tray. The amine then absorbs the H2S and CO2 from the gas before it rises into the next tray, where even more of these compound chemicals are absorbed. By the time the gas gets to the top of the column and is discharged, most, if not all, of the H2S and CO2 should be removed. At this stage, the sour gas has now turned into sweet gas, and is ready for sale or further processing. Meanwhile, the liquid amine solution enters the column from the top and collects H2S and CO2 as it makes its way downwards. By the time it reaches the bottom, it is already full of these acid gases, and is known as rich amine. Instead of discharging these rich amines, it is pumped to the stripper column, where the acid gases in the amine solution are stripped, and the amines reused. The rich amines enter the stripper column from the top. The liquid falls to the bottom, while the vapor rises to the top, where it passes through a condenser before discharging the acid gases. Any liquid that is caught in the condenser is then pumped back into the stripper column. The rich amine fluid at the bottom of the stripper column makes its way into a reboiler. Here, the liquid is heated up, releasing any acid gases in the solution and converting the rich amines into lean amines. The lean amines are then pumped back into the absorption column, where the cycle of gas sweetening begins once again, while the vapor from the reboiler re-enters the stripper column, rises to the top and through the condenser, and is finally discharged. A system like this is effective and efficient. It can cut costs since the amines never leave the system, it simply circulates.
So in this video, we have seen that how that sour gas, we generally call it as, which is nothing but the natural gas stream containing the acid gases. It will be passed through an absorber, where the acid gases will be absorbed by the amine solution, or the which we will call it as a lean amine solution. The acid gases will pass to that amine solution, will be then removed by using a distillation column or a regenerator, we will call it as, and the lean amine solution is put back into the absorber column. So here we have seen the two concepts, which is called as lean amine solution and rich amine solution. So it is with so it is with acid gases, and it is not containing any acid gases into it. So this is just the for your understanding purpose. Now let's move ahead towards the acid gas treatment plant exercise. So in this plant exercise, we are basically using the absorber, which is used to remove the contaminants from the natural gas through absorption into a MDEA stream, that is methyl diethanolamine stream. So we will be using amine as MDEA, that is methyl diethanol amine. The MDEA flows continuously from the top to the bottom of the column. Natural gas will bubble upwards through this amine. Carbon dioxide and hydrogen sulfide will transfer into the amine phase during this process. A valve is used to control the liquid flow from the absorber and supply the pressure drop. A lean or rich heat exchanger will preheat the rich amine. See, previously, like what we will be doing, we will be first simulating this without a recycle. We will just check what outputs we are getting in terms of concentrations. Then we will be introducing the recycle into the system, and we will see what differences in the output have been observed. So this heat exchanger part we will be using while are going through the with recycle exercise. Before for this without recycle exercise, we will be simply using a heater just to preheat this feed to the regenerator. So a lean or rich heat exchanger will preheat the rich amine solution before it enters the regenerator. The hot lean bottom stream will occupy the tubes, and the cold rich amine stream will occupy the shell. As we have seen in our shell and tube heat exchanger, there are some criterias for setting the fluids, like which fluid should occupy the shell, which fluid should occupy the tubes. So at that point, we have seen that the hot liquid should occupy the tubes always, and the relatively less hot or cold liquid should occupy the cell. So we will be following that rule over here. The regenerator will separate the acid gases from the amine through distillation. Acid gases will be removed as the distillate, and the bottoms amine will be recycled for use in an absorber again. A surge tank, which is also called as a makeup tank, which supplies the makeup water and amine to return it through the amine to desired strength. An optimal slipstream can be removed from the surge tank. This would prevent the buildup of impurities in a real acid gas treatment process. The pump and cooler are further used to return the amine to the desired temperature and pressure for use in the absorber column again. The recycle block is used, which allows the simulation system to converge on a recycle loop. You must remember that while using the different logical operators in Aspen HYSYS, we have not covered the recycle block. So in this example, we will be just covering the application of recycle loop. So this is just the, you can say, the flow sheet that we are going to solve in the first part of our today's session. It is without recycle. You will see that there is an absorber first. Here you can see this is the absorber, which is given an input of lean amine and the feed gas, from which the sweet gas or the gas which is almost free from, I will not say it is like 100% free from acid gases, but it is almost free from acid gases. It will be taken out from the top of this absorber, and the bottoms will be passed through a wall just to give the required pressure to a separator. The function of this separator is to remove the light hydrocarbons, if any, and pass that lean amine to this heater, where it is preheated before it is passed through a regenerator, which is basically a distillation column, from where you can see that these acid gases are taken out, and this is the lean amine stream, which is again recycled back. But in the first part, we will not be going, or we will not be checking for any recycle operation or the recycle part. After completing this, we will just see what concentrations we are getting over here, here, and here. So after that, we will just replace some of the equipments, like we will replace this heater with an heat exchanger, and we will see how we can form a recycle system into this. So this is just the steps, because though it is not having any predefined problem statement kind of thing, like it will be in your certification examination also, they will not be giving you the uh, problem statement, like they will give you like this, and then they will give you step by step values like this, and you need to just uh, stimulate the things. But the most important thing over there, or at that point of time, is you should know where which things should be entered. So for that reason, I'm just telling key, please be concentrated while attending the sessions. If you have any doubt, like which value is given over where, like in which tool or in which menu this value is given. If you have any kind of doubts like this, please do stop me at that point only and ask me to repeat the things. Okay. So I will just request you to take screenshot of all the screens which I will be going through from the steps from now on. Just take a screenshot of all the screens. It will be required for you while we are solving this. Today's first part of the exercise, I will say. Second part, I will give some time for you to take screenshot after this. So please take a screenshot of all these screens while I am explaining these steps. So we will be adding different components. Like first our methyl diethanolamine, that is MDE amine, then CO2, H2S and H2O. Then we will be adding some hydrocarbons like methane, ethane, propane, ibutane, n-butane, ibentane, n-pentane, just to simulate the natural gas stream. Now we will be selecting one fluid package, which is acid gas chemical solvent. I will be demonstrating you like why this particular fluid package is only selected for this particular simulation. Then we will be entering into the simulation environment. There we will be first simulating two material streams. The first one is natural gas feed stream, and the second one is obviously lean amine feed stream. These are the conditions and the compositions for the natural gas stream as well as the lean amine stream. So take a screenshot of this as well. Then we will be adding an absorber. These are the specifications given for the absorber. Like it is having 20 number of stages. Then what is the top stage pressure? What is the bottom stage pressure? Everything is given. The absorber will be followed by a control valve, which is basically a valve having a outlet pressure of 70 psi. Just the wall, the purpose of this wall over here is to reduce the pressure before it is passed through a separator block. Separator block, it is nothing but a two-phase separator we will be using for this purpose. And we will be mentioning a delta P inlet for this particular separator block. From this separator block, the liquid part we will be passing through a heater just to have some preheat, preheating the field before it is passed to a distillation column. Then in the last part of this first, like without recycle part, we will be using a distillation column and we will be calling it as a regenerator column. And these are the specifications that are given for that distillation column. I will just request to take a screenshot of this as well. After finishing this part, we will be completing with our without recycle flow sheet. We will be just giving some specifications for this regenerator column. These are the specifications that has to be given for that regenerator column to get simulated. After that regenerator column, we will be, this is our final exercise with recycle. Here you can see our heater, it was replaced by this. Just ignore about this part. We will not be covering because this is just the additional part. So we will not be taking into account this part. This is just a heat exchanger, which is the shell and tube heat exchanger that we are using. You will see that here we will have a surge tank or makeup block. I will tell you how to add and simulate this surge tank or makeup block as well. You will need this surge tank or makeup block in many of the examples when you are going for real-time process simulation. So we will see that part as well, how to add and how to simulate a makeup block or surge tank. Here we will use a booster pump, which is basically a centrifugal pump followed by a cooler, just to bring the stream to the desired temperature and pressure so that it can be added to this lean amine stream again. Here you will see that different streams are having, because generally you can see that different streams or the material streams will have blue color and the energy streams will have red color like this. This all material streams are dark blue in color and all the energy streams are dark red in color. But here you can see that there are different colors based on this temperature ranges. So in the today's session, we will see how this temperature ranges can be applicable, because what happens is like sometimes in the your process plant, you need to show to the customer or to a person who is not understanding or who is not having that much understanding of this Aspen HYSYS part. You will have to represent like this line is having this much temperature range and all that. So for that purpose, this is quite useful, because you will see that if the temperature is less than 128 Fahrenheit, it is shown in dark blue color. So you can just clearly identify these lines are having the temperature less than 128 degree Fahrenheit. So like this, we will be learning that part as well. So before going for this recycle part, let's just simulate this acid gas treatment plant without any recycle. So I will be going very slow for today's as well as tomorrow's exercise, because if you may think like it is looking very simple, but if you make a single mistake in entering any of the value or any of the specification, it can cause the results to change like anything. It can cause the acid gases to come into that sweet gas part in more extent if you give some wrong specifications. So don't ever do that. Just try to get like the things in a very precise manner. For that reason, just go slow and try to incorporate all the conditions that are given into the problem statement. So we will start with our today's session of this simulation. Let's start with a new case. I will be adding the components one by one. Before doing that, let me save this case as acid gas treatment plant. So let's add the components. So what are the components given to us in the problem statement or the steps? Let's add first MDE amine. So I will just write over here MDE amine. So this is the MDE amine which I'm going to select. Then the second component is CO2. So I will select this one. Then H2S, that is the hydrogen sulfide. Then we have H2O, that is water. And then we have our hydrocarbons starting from methane, ethane, propane, ibutane, n-butane, ipentane, n-pentane. So we'll just go by this sequence: methane, ethane, propane, ibutane, n-butane, ipentane, n-pentane. So we are done with adding the components. Now we will go for selecting the fluid package. For this particular example, I will be using my method assistant for selecting the fluid package for this. So I will just click on this method assistant. and a help window will appear in front of me. Now I will just see what my process exactly falls under any of these categories. Like it is a oil and gas processing, refining, it's a chemical, it's a clean fuels, electrolyte, environmental, mineral, metallurgical, petrochemical, or power. So our process falls under the first category, that is oil and gas processing. So let's click on that. In general, we recommend to use that cubic equation of state-based property package for this, like Peng Robinson CPA. Select the process that you are modeling for further assistance. So our process is gas treating process. So let's click on that. So it will give me the further classification of gas treating process, like whether my process is glycol dehydration, sour water, sulfur recovery, or acid gas treating process. So our process is acid gas treating process. So you can see that it will be giving you the direct fluid package for that particular process. So here you can see that our fluid package is acid gas chemical solvent. Let's see over here what is recommended by that. See, you can see that to model chemical or the amine solvent with liquid gas systems, our is the liquid gas system only use acid gas chemical solvent as the property package. To model physical solvents, if any physical solvent is involved in that, you can go for acid gas physical solvent. To model amine solvents with liquid systems, ours is not a liquid systems, ours is a gas liquid system. If it was a liquid system, then we might have gone for this acid gas liquid treating process. To model a caustic wash process, you can go for acid gas caustic wash process. So let's click on this and let's see. The acid gas chemical solvent property package is used by Aspen Assets for acid gas cleaning during the fluid package setup. This is all the information given about that fluid package. You can just go through this in your free time. So the property package which is suggested by us is suggested to us by Aspen Assets is acid gas chemical solvent. So let's select that. You know, one beauty of this Aspen Assets, if you will see that when I will directly click on that fluid package, as I have selected this MDE amine and my component list is containing CO2 and H2S, it will by default or it will automatically select the property package for me. I will not click on any property package. You will just see if it senses that it is having some amine, CO2, H2S, water, it means that amine plus water, it will be forming that amine solution. It is having these two acid gases, CO2, H2S, and a natural gas stream containing this. It will by default select that fluid package for me. Let's see how it is done. I will just click on fluid package. I will not select any package based on that. Add. And you will see that it will by default select that property package. You will see that acid gas chemical solvents. Chemical solvents CO2, H2S, H2O. So I've told you, okay, it requires these three components, CO2, H2, H2O, and any of these supported amines. Like we have selected this MDEA. I have not clicked on any single property package. I have just clicked on add button and it has directly added that property package by default for my selected list of components. But as I told that, don't blindly go for the property package which is suggested by Aspen Isis at any point of time. That's why I have, before coming to this step, I have shown you like how we can use this method assistant to select which property package is correct for our process. This was the property package suggested by the method assistant, and the same property package is selected or is chosen by Aspen Isis for our process. So we can blindly go for this property package selection, that is acid gas chemical solvents. Now we don't have any reactions, we don't have any petroleum assays, we don't have any user properties to be added. We can directly go to the simulation environment now. Going to the simulation environment. It's taking some time. Okay. Now the first thing that I will do is I will just add two material streams. One and two. The upper one, I will be simulating it as a lean amine stream. For which the conditions are given. See, for my system, the temperature is given in Fahrenheit, pressure in PSI, so it's better that unit set should be selected as field. So the temperature for this lean amine stream is 110 Fahrenheit, 110 Fahrenheit. Pressure is 824.7 psia, 824.7 psia. Then we have the standard ideal liquid volume flow of 100 USGPM. So we'll just enter this value as 100 USGPM. And we are given with the composition of this lean amine stream as MDEA, because this lean amine stream will contain only amine and water because it's an lean amine solution. So amine is 45%, that is 0.45, and the water is remaining 55%. Click on OK, and this lean amine stream will be now simulated. Similarly, we will simulate the feed stream. We'll call it as natural gas feed, for which the temperature is given as 100 Fahrenheit. Pressure is 824.7 psia. Molar flow is given as 100 mms CFD. Sorry, 10 mms CFD. It is not 100 mms CFD, it is 10 mms CFD. And the composition for this stream is CO2 is 0.05 mole fraction. H2S is 0.025 mole fraction. Then methane is 0.8250 and ethane is 0.1 mole fraction. So we are done with this two material stream simulation. The first one is lean amine and the second one is the natural gas stream. After this, we will be adding an absorption column into this. We'll go to the separator section. We'll take an absorber. We'll add to our simulation area. Double click on this absorber. We'll rename it as absorber. The top stage inlet should be my liquid solvent, that is lean amine stream, and bottom stage inlet should be my natural gas. The number of stages are 20. My overhead product will be sweet gas, and bottom liquid will be to the next equipment, that is to wall. So we will give the naming like this. Whenever we are simulating any flow sheet, we will give the stream which is going to any next equipment. Suppose if it is going to a heater, we will rename it as to heater. If it is going to a wall, we will rename it as to wall. Now the top stage pressure and bottom stage pressure for this are given as 814.7 psi at both. Like we will enter those values 814.7 psi. Similarly for this 814.7 psi. And click on next. We are not known with any temperature estimates. Obviously it is optional only, so we are not going to give that value. My tower is now ready to run. I will just click on run and it will be converged. I will close this and I will just open this sweet gas stream. Maximize this for you. Go to this composition and you will see that there is very less mole fraction of this CO2 and H2S. It is there into this sweet gas stream. You will see that my MDE amine, it was completely removed, or it is completely removed. That is 0. So this amine stream will be going into the bottoms of this absorption column. So there is no amine which is there into this sweet gas stream. Now the next part is we will add a wall to this. We'll add a control wall. Double click on this wall. Just rename it as wall. Inlet is 2 wall. Outlet is, because after this we will be adding a 2-phase separator, so the outlet will be 2 separator. Unknown delta P, we will go to this worksheet part and we will mention the outlet pressure as 70 psi, because we need to have the stream pressure of the feed stream for the separator is as 70 psi. So give that value over here and our wall is now converged. We will add the next part, that is a 2-phase separator. Just rename this as separator. The inlet will be 2 separator. Vapor outlet stream will be light hydrocarbons. And liquid outlet stream will be 2 heater, that is for the next equipment. Now here they told us to add one additional parameter, delta P inlet at 35 psi. So where we can add that, we can go to this design tab, parameters, delta P for inlet is 35 psi. So we will just give that value. This is an additional design specification that they have told us to add in this. So we have added that as well. Now the next part is we will add a simple heater. Double click on this. Rename it as heater. For this, the inlet is 2 heater. Energy is 2 heater and outlet will be 2 regenerator, because after this we will be using a regenerator column. So 2 regenerator we will be giving as an outlet for this heater. Now it is showing unknown delta P. So we will just enter the pressure drop for this heater as into this parameter tab. Delta P is 5 psi. Unknown duty. So we need to give the outlet stream temperature as well. So this temperature is 200 Fahrenheit. So we will be heating the stream from 134.7 Fahrenheit to 200 Fahrenheit. This is the, like we can call it as a preheated feed, or we are preheating the feed which is being fed to the regenerator. That is basically a distillation column. Now we will just add a distillation column. Go to the separators. This is our, sorry, this is our distillation column. This is just a three-phase separator. This is our distillation column. Just double click on this. Column name is distillation column. We will define the energy streams for condenser as Q condenser, and similarly for reboiler, we will define the stream as Q reboiler. This column is having number of stages as 20. So we will just enter that number. Stage numbering is from top to bottom. So we will be going it by default. The feed stream is 2 regenerator and it is entering at stage number 3 from the top. So we will select that stage number 3 as the feed stage. Then this is going to be a column which will run on full reflux. So only vapor product we will be taking out from this. The overhead vapor product will be the acid gases, because we don't want to lose any of our lean amine solution as a product, or we are not going to take any part of that amine solution which is regenerated from this as a product. That's why we are putting this column onto a full reflux type of condenser. And the bottom product will be, we will simply call it as from regenerator. Then we will go to next. We will be going with regular burst through high C3 boiler. We click on next. The condenser pressure is given to us as 22 psi. Then the condenser pressure drop is 2 psi. Reboiler pressure drop is 0.1 psi. Sorry. And the reboiler pressure is 26 psi. We'll go to this next. No temperature specifications we are giving right now. We click on next. No vapor rate or the reflux ratio we will be giving for this. We'll click on next, click on done. We have, see, whenever you are trying to run a distillation column, always check that here the degrees of freedom should be 0. If it is 1, you are missing with some information that has to be given for running the distillation column. Even though if you have this degrees of freedom as 0, we are not given with any value over here. You can see that no reflux ratio value is given, no overhead vapor rate is given, no reflux rate is given, no bottom product rate is given. We'll try to run this column. One or more specification in the column flow sheet is not fully defined. So done. Either we need to enter the reflux ratio value or we need to enter the overhead vapor rate value. So without giving any of the specification, we cannot run this column actually. So for that reason, we are given with 2 specifications. One is column duty and the second one is column temperature. So we will add those 2 specifications to this column. The first one is column duty. Add specification. This duty is for reboiler, the energy stream. So we will select it as Q reboiler column 2. And the value is given as 6 MMBTU per hour. That is MM, British thermal unit per hour. We'll cancel this or we'll close this. You can see that our specification is added. We'll add one more specification, which is in terms of column temperature. We'll add specification. The column temperature is for top condenser temperature. So we will just select this as or rename this as top condenser temperature. Stage, we will select it as condenser only because we are going to give the value for this condenser temperature, and the specification value is 115 Fahrenheit. Now we will run the column with these two active specifications. You will see that active, we will make uncheck these two and we will check this two. We'll click on reset and run. Before I'm doing that, it has started the solving part of that column, and we will see how much time it takes. You will see that in this window how many sorry how many iterations it is doing. You will see that in this window it is now it has gone to 131, 151, in like 161, 170 iterations till now. Still it is not solved. You can see that the status is still solving. It's not solved. Now you can see that the iteration number has gone to 300 almost. Still it is not solved. When this is solving this, you can see that the current values are for these two, as we have given these as specifications, it will not be changing. You will find that this values for the reflux rate, overhead production rate, then the reflux ratio, bottoms product rate, it will be changing like with every iteration. You can see. Even though it's a minor change, but you can see that the values are changing. We'll just wait till the iteration 600, and if it is not, we will stop this. You can see that the iterations has now gone beyond 600. We will just stop this and we will just make one simple change. Like we will go to this parameters, go to this solver. Here you will find that what are the maximum number of iterations it can go to. 10,000, you will see that it can go up to 10,000 iterations. So if we would have wait for that purpose, it would have completed that 10,000 iterations, and after that still it has shown that it might have shown that it is unconverged. Now here we are going to give one value. Whenever you will just keep in mind that whenever the flow sheet is not solved, always do that one change is this heat specification error tolerance and equilibrium error tolerance. These two should have the same values. You can see that this equilibrium error tolerance in our case now is 1 into e to the power minus 5, whereas this heat or the specification error tolerance is 5 into e to the power minus 4. So we will give this equilibrium error tolerance as well, this value 5 into e to the power minus 4. This is just a simple adjustment we are doing for solver. There is no hard and fast rule behind that. It is just a adjustment. You can say it like we are making just in order to uh, get our system converged, because these two should not have different values. when the system is getting converged without changing this value, let it be. You will not require to change these two values. But when the system is not getting converged after a certain number of iterations like 500, 600 and all, you can just go for changing these values. So we have changed this value now. Now we will reset and run the column and we will see whether it is getting converged or not. You can see that the column has got converged within 7 iterations only. It has got that value of error tolerance of equilibrium error. You might have seen that the equilibrium error. I will just enter that value again. What is the value we were having previously? 1 into e to the power minus 5. And we will see that you can see that this equilibrium error value is in the range of to the power minus 4 or to the power of minus 3. Everywhere it is happening. So for that reason, we have kept these two values as the on some equal value, that is 5 into e to the power minus 4. This was the reason behind changing this value. So we'll just click on reset and run. We will see that within, like, iterations may go from 5 to 10, 11, but it will be converged easily, or it will be converged very quickly. You can see that my reflux ratio value is 3.724, overhead vapor rate is 41.65, reflux rate is 155.1, bottoms product rate is 807.7, and temperatures are like whatever the specifications I've given, it is on more or less that value only. So our flow sheet is now converged without any recycle done. Now we will check this acid gas stream for the composition. We'll go to this acid gas stream, check for the composition part. And you will see that in this acid gas stream, so there is CO2, there is H2S, and there is some part of H2O is there, that is entrained with that vapor. So there is some part of H2O, or we can call it as the in the form of steam. There is some part of water is there into that acid gas stream. So we can say that like there is no amine, there is some part of methane as well. You can see that, sorry, ethane. Some methane, some ethane is also there. So you can see that like we can say that it has not completely an acid gas stream, but like to more extent it is containing acid gas stream, acid gases only. Why it is happening? Because we are not putting yet put this system onto the recycle. In the recycle part, if you put this system on recycle, what happens exactly is it will keep on running the systems, or it will keep on passing the things through that system. So that will uh, what we can say, that will add some efficiency, or that will improve the process, and it will also affect on the end results, like the acid gases concentration or the composition will be something different, the sweet gas composition will be something different if we put the system on the recycle. Now what we will do is we will just check this, which we have checked previously as well. The CO2 and the H2S are there in small extent into this sweet gas stream, that should not be there. Also similarly in this acid gas stream, just check the composition of H2O is there, methane is there, and ethane is there. So now what we will do is we will just try to put this system onto the recycle and we will see what difference it will cause. Let's check for this from regenerator stream as well, because it should contain the amine and water. You can see that here there are no acid gases. It is containing only amine and water. So it's from regenerator stream, which we are going to use for recycle. It's perfectly ideal. You can say that no other component is present in that stream. No acid gases, no any natural gas, only amine and water. So this gas stream or this stream is ideal for recycle. You can say it like that. So I hope you are clear till this, or anything which you would like me to repeat, any part, any equipment, please let me know now only. If it's clear, we can go ahead for recycling the stream or recycling the system. Can we go for the recycle part?
Yes, sir.
Okay, great. Sure. Thank you. So I'm understanding that everything till we have done till now is clear to you. Now we will go for this recycle part. In the recycle part, what we are doing is we are going to simulate this one. This is just the extension of what we have done till now. You can see that absorber is there, wall is there, separator is there, and this regenerator, and or what we can call it as the distillation column is there. The only difference is just this heater is exchanged by this heat exchanger. We have added this makeup block, booster pump, and the cooler. So these are the next steps. We can call it as remove the heater before the regenerator column and add a shell and tube heat exchanger. These are the inputs for that shell and tube heat exchanger. The heat exchanger model that we are going to use is a simple bed model. The shell side pressure drop, tube side pressure drop is given to us. We will be adding a makeup block. I will tell you how to add and simulate a makeup block. That is very simple thing, but you should know most of the things. You might have seen many of the YouTube videos that are available on Aspenisis, but nowhere they have explained like how to add a makeup block and all that thing. So we will see today how to add a makeup block. It is very simple thing, but in this makeup block, if you make a single mistake, that will not converge, and what that will do, that will close your entire flow sheet. It is like that kind of difficulties there with that makeup block. If you don't configure it properly, it will not converge your system, and you will close your HYSYS. So that's why you should have uh, more concentration, or you should concentrate more while adding this makeup block. I will tell you how to add this makeup block correctly. So take a screenshot of these two things as well. Right from this, take a screenshot of this plant with recycle. Take a screenshot of this as well. Take a screenshot of this. And following the makeup block, we will be adding a pump and a cooler. After this, we will be simply adding a recycle operation. And then we will see how the stream colors are added based on the different temperature ranges. Before going for this, let's have a quick view on what we are going to change into this recycle stream, or like what changes we are making into this recycle when we are going for this recycle operation. The first change we are going to do is we are replacing heater with a shell and tube heat exchanger. I'm just writing the short form, shell and tube heat exchanger. Second thing is we are going to add a makeup block, or we can call it as a search tank. Then we will be adding a pump and cooler. So I will just tell you what is the purpose of behind adding all these three things. First thing we are going to do is we are replacing this heater with a shell and tube heat exchanger. So for this heat exchanger or the shell and tube heat exchanger, the purpose will remain the same. It is for preheating the regenerator fluid. It is just for preheating the regenerator fluid. So we will be passing it to the shell and tube heat exchanger, and the output of this heat exchanger will be given to that distillation column. The from regenerator stream, which is passing or which is coming out from the distillation column, which is at a higher temperature, we will be passing it again to the heat exchanger. We will be taking out that heat from regenerator stream and passing it to the regenerator column feed. So we will be, by doing this, what we will be doing, we will be forming a heat exchange network between the regenerator feed and the regenerator product. So the regenerator feed, which is to be given to that distillation column, is heated itself by the product of that regenerator. So we will be just using that heat to heat the regenerator feed. So we will be forming a heat integration or a heat exchange network by doing this. So the outlet of this heat exchanger is then set to a makeup block. The one outlet will be sent to a regenerator and the second outlet will be sent to a makeup block. This makeup block will be adding some extra amine or water which is required to make up that MDEA amine stream so that it can be recycled back into the system. And so this is the purpose of this makeup block. And why we are adding the pump and cooler? Because the stream has passed through many of the equipment. So its temperature and pressure might have changed to some extent. So in order to bring back to like whatever the temperature and pressure for that stream to the value which is matching with that lean amine stream, because we will be adding that stream again to that lean amine stream. So just in order to cope up with the pressure and temperature values, we will be adding the pump and cooler after this makeup block. So we will be now simulating these things. First, we will be replacing the heater with a shell and tube heat exchanger. Then we will be adding a makeup block, and then we will be adding a pump and cooler. So we will just go for the HYSYS window. Now what we will do, the first part, that is we will remove this heater. We'll select this heater and delete this one. We want to delete heater? Yes. Whenever you will delete any equipment, just please make sure that you will be deleting all the associated streams which were associated with that deleted equipment. So here you can see that this energy stream, it was associated with the heater which was not deleted. It will not be deleted. You need to delete it manually. Now I have deleted the heater and all the streams that were associated with that heater. Now we'll add a shell and tube heat exchanger over here. We will call it as simply a heat exchanger. For that, the tube part inlet will be, tube side inlet will be to heater. The tube side outlet will be, because we are passing the hot fluid through the tube, so the fluid which is getting heated, that is to be fed to the regenerator. So the tube side outlet will be from regenerator. Shell side inlet will be the hot fluid coming from this is which is from regenerator. That sorry, it's to regenerator. It is not from regenerator. We are passing it to regenerator. That's why shell side inlet will be from regenerator, and shell side outlet we will be giving it to the makeup block. So that's why to makeup. So we have defined all the inlet as well as outlet streams. Now the heat exchanger model that we are going to use is simple bed. We will go to this parameters tab. We'll select the heat exchanger model as simple bed model. The specified pressure drop at the shell side is 2 psi. So we will just mention that. And tube side is 5 psi. So these are the specifications. Now you can see that our heat exchanger is now converged with all the streams, but it is still showing that error, FT correction factor low. We have discussed this error. Go to this performance tab. You'll see that this FT factor is 0.698, which is low. So that's why it is showing that error of FT correction factor low. So let it be. This is just a warning. This is not an error, or it is not causing our simulation to stop. So let's not worry about that at this stage. And we will go ahead with the further simulation. Now what I will do is I will just make this heat exchanger flip a little. I will just flip this heat exchanger a little bit. We flip it vertically so that it will be arranged in such a way that I can pass it to the makeup. I will just move this stream to makeup by 90 degrees Celsius so that it can be pointed upwards. Now the next thing that I'm going to do is I will be adding a makeup block. So I will be just typing makeup over here, or I will just type make. You will see that this makeup block will be appearing over here. I will be just changing its rotation. We will be flipping it horizontally. You will see that there are three streams that are associated with this purge, so that if it is having any gases, it can be removed from this purge stream. It will be adding one water stream and one MDEA amine stream. I will just open this makeup block. We will just rename it as makeup. That's it. The inlet stream will be to makeup, which is coming from that shell and tube heat exchanger, and outlet amine stream. It is we are passing it to the next equipment, which is a pump. So the outlet stream we will be defining it as. Now, as I told that this makeup block has to be configured very carefully. We are given with the value of amine concentration as 45%. So what most of people do is you should not touch these two streams unless and until you have any of the other stream which is to be supplied from as an add-on. We are not, in this example, we are not going to supply any add-on stream. We will be using the default streams which are for water and MDA. What most of the people do is the amine concentration for MDA amine is given as 45%. So what they will do, they will enter that amine concentration of 45% over here, and it will cause that makeup block to go into some ROM calculation modes, and it will not just stop your simulation, but it will close your HYSYS, because it is going to be into an infinite calculation loop. So please don't do that. Whenever you are asked to like enter the value for this outlet stream amine concentration, you should enter that value here, not here. It is 45%. You can see that. One more information is given to us is total flow in terms of liquid volume standard condition is 100 USGPM. So you can just enter the total flow in the term in the form of mass flow, molar flow, or liquid volume at standard condition. It is 100 USGPM. And that's it. It should be solved. So just one error of entering this value over here, it will not just stop your simulation, plus it will entirely close your HYSYS because it will be putting your makeup block into an infinite calculation loop. So that will hang the software and it will close the HYSYS. So don't ever do that. Don't touch any part of this rating worksheet unless and until you have the values available with you. So this is the precaution that you need to take whenever you are simulating this makeup block. Unless and until you are given with any value, don't touch the defined value or the default value for that particular parameter. Now we will add a centrifugal pump. I will change the rotation of this as well because we are simulating a recycle loop. That's why we need to change the rotation or the orientation of each and every equipment. I will rename it as pump. The inlet will be two pump and outlet will be two cooler because after that I am adding a cooler. Energy will be two pump. And for this pump, if any other information is given to us, no. So let this be like not simulated. We'll close this. We'll add a cooler after this. And we'll rename it as cooler. The inlet is two cooler. Energy stream will be two cooler. And the outlet will be, we will be passing this outlet to the recycle stream. So to recycle unknown delta P. For this cooler, the pressure drop is given as 0 psi. We will just enter that value and the outlet stream temperature and pressure values are given. Temperature is 100 Fahrenheit, oh sorry, 110 Fahrenheit. Because we need to match these values to the lean amine stream temperature and pressure values. That's why we will be giving the same values 110 Fahrenheit and pressure is 824.7. You'll see that my pump is also now configured. I will change the orientation of this cooler as well. Now I will simply add a recycle block to this. It is there in the manipulators. This is the sign for this recycle block. And in this recycle block, you just need to give two things. One is inlet and one is outlet. The inlet for this is to recycle. And the outlet will be our lean amine stream. As soon as I give this outlet, it will be going on a not solved mode. It will take some time to solve because it has to calculate different values for this. That's why you will see that it will take some time to solve. And now you will see that our entire system is now converged. Just arrange it in such a way that you can see the system in a one go. You will see that our entire system is now, even though it is looking like a very complicated system, but you have seen that if you go equipment by equipment, one by one, it will never be a difficult thing to calculate or to simulate anything. Just try to like take a step by step approach. Take one equipment, give all the specifications correctly. Even though it is not solved, try to give all the specifications correctly. Go for the next equipment. You will see that might have seen, you might remember that while doing that uh, propane refrigeration loop wala example, the entire loop was not solved unless and until I have not added that final wall. So it will be like that sometimes. If you add the last equipment, it will cause all your flow sheet to solve in one go. So just try to give the things in a very precise manner, and you will find that your entire flow sheet will be simulated. Now we will see like what difference this simulation has caused. Go to the sweet gas stream again. Have you remember like these two values? You will see that these values H2S, it has now become 0. Previously, it was having something value around 0.0010. Now you can see that the H2S is completely removed, and the mole fraction of CO2 previously it was something around 0.06 or 0.3, something like that. Now it has gone to 0.0073. You can just point out the difference, like these two values have changed like anything. H2S has become 0. Now we will go for that acid gases part as well. Go to this composition and you will see that here also you can find some difference in the values. This acid gas extent it has increased, and rest of the things, obviously there will be some methane and ethane, but you will see that the extent of methane and ethane is also very less. This H2O, that is the water in the form of, maybe it is in the form of steam. You can see that this water extent is also reduced. It should mostly contain these two components only, CO2 and H2S, and you will see that that extent has now increased as compared to previous value. So this just we can think of the conclusion like we have put our MDEA amine into this recycle. We will be recycling this amine stream, and you will see that there is a difference between that sweet gas stream, that is this stream, and acid gas stream in terms of respective concentrations of those particular components. Because in the acid gas streams, you should have more extent of CO2 and H2S. There should be less extent of other components. And in the sweet gas stream, there should not be any H2S and CO2. You might have observed that the H2S was completely removed, and CO2 present also, that was there into some 7.6 mole fraction or something like that, 0.76 mole fraction or something like that, 0.0073. So that is also to very less extent. This difference has happened because we have recycled this MDEA amine into this. So clear with this? Or if you want me to repeat any of the equipment, any of the simulation part, which is not understood to you, please let me know.
Just repeat the absorber section quickly.
First part, you want me to repeat?
Yeah, yeah, yeah.
Okay, no issues, no issues. What I will do is I will just save this case. I will open a new case, add the components quickly so that you will get an idea. Because if I will remove the absorber now from the system, it will recalculate everything and again it will go into an unconverged mode. So I will just add the components quickly again. I can try it for it will be selected. We'll go for the simulation part. Add the materials to used. This is the Lehman. Temperature is 110 Fahrenheit. Pressure is 824.7 and standard ideal liquid flow rate is 100 USGPM. Composition is DEMI is 0.45 and water is 0.55. Similarly, we will simulate this natural gas stream. Temperature is 100 Fahrenheit. Pressure is in same 84.7. Molar flow rate is 10 mms CFD. The composition for this is Newton is 0.05, yes, 0.045. Sorry. And methane is 0.8250 and ethane is 0.5. This is about the material steps. Now we'll add an absorber. Top stage inlet will be lean amine because liquid will be coming from top to bottom and gases will be bubbling from bottom to top. So bottom stage inlet will be natural gas feed. The number of stages are 20. For this, the overhead vapor will be sweet gas. So we will define that as sweet gas. And the bottom liquid will be to the next equipment, that is to wall. We click on next. We are given with the top stage pressure and bottom stage pressure as 814.7. Same is the value for the bottom stage pressure. We click on next. There is no temperature value that we are going to give for this. We click on done. We will run this column and it will be converged. You can see that it has taken 10 number of iterations to converge the system. I hope you have understood this absorber part.
Amine flow, have we put or is it calculated?
No. Amine flow, we have given the value.
But if we
It has,
want to calculate it, then
we want to calculate it. No, actually,
yeah.
see, whatever the feed values are there, that has to be
Mhm.
given. Because for any of
Okay.
the material streams, we need to give the temperature pressure, and any of the flow values. So these three things are compulsorily that we need to be given.
Okay. Okay.
So we will open our exercise again. So this was the thing which we have calculated or which we have simulated just right now. You might remember one sentence like which we have seen while having the overview of this recycle operation. Recycle can work in both the directions. It can work in forward direction, also it can work in the backward direction. Now we will be using it in forward direction. Like even though it is in this direction, it is a forward direction. Like from this point to this point. That's why we have not changed anything over there. But if you want this recycle operation to work in a backward direction, you can change this to backwards or not transferred. This is just the nil kind of thing. Like you are not using that vapor fraction to be transferred from, you don't want any of your this things to be transferred into not to be transferred from one equipment to another equipment, then you can just select this as not transferred. If you want that parameter to be transferred in the forward direction, you can select this forward. If you want to transfer that parameter into in the backward direction, or if you want your recycle loop to work in a backward direction, you can select that as well. And these are the sensitivities. Like if you want that parameter to change in a very sensitive matter, you can give it to the highest value. If you want the sensitivity to be at the lowest value, you can just lower the value or the lower the sensitivity. There will be one example on this part as well, maybe in the next or next to next session. So during that example, you will just understand how this sensitivity values will be changing. For the time being, uh, mm, uh, just understand like this transfer direction, it will be just an indication of in which direction your recycle loop is working, and the sensitivities like how that how you want that particular parameter to change sensitivity, like sensitively with respect to your recycle loop. Just keep in mind these two things as of now. You will get more understanding for these two things when we will be solving an example based on this. It will be there in the next or next to next flow sheet. So this is about this acid gas treatment plant. Now there is one part or the last part of this today's session remaining is how we can change the default color schemes for this. Now you will see that every material stream you can see in the dark blue color, and every energy stream you can see that it is in dark red color. But if I want to change, as we have previously discussed this thing in the first part of our today's session, if I want to pass or I want to give this flow sheet to a person who is not very much familiar, or he will not be having time, or he will not be taking efforts to open each and every stream or show table for each and every stream and check what is the temperature, he just wanted to have an overview of what is the temperature range of my different streams that are there into my flow sheet. So at that part or at that time, you can just represent your different material streams into different colors based on temperature ranges. So how you can do that is just click outside, anywhere outside your flow sheet into this blank part. Go to this flow sheet or modify menu, firstly you need to make sure that you are not clicking on any equipment. Otherwise, it will just apply that to that particular equipment only. You just need to click on anywhere outside this blank part of this simulation area. So that by doing this, what you are just ensuring is you are not clicking or you are not selecting any particular equipment. Just click anywhere outside this blank part and go to this flow sheet and modify. In this last part, which is conditional formatting, you might remember that in your Excel as well, there is this command called as conditional formatting. There you used to highlight your values by giving the different color ranges. Suppose if I am having the marks of 10 of my students, I will be uh, like dividing that marks into different colors. Like suppose if I wanted to highlight the students who are having the marks between 30 to 40, that should be highlighted in red color because they are in the fail range. So for 40 to 50, some different colors, or from 50 to 60, some different colors. So that is the purpose of using this conditional formatting feature. So here in Aspen HYSYS as well, you can use this conditional formatting feature like this. So for this reason, what you need to do, just go to this editor and you will see that different colors are there into this system. Here you can see that you will have 1, 2, 3, 4, and 5 categories, or the 5 sections in which you can select your color ranges. You can give with the default color scheme, HYSYS color scheme, dynamic pressure flow specifications, temperature, CO2 freeze out, hydrate formation, free mercury, or add new. Just click on this add new. You will see that you can add any of the variable which is there into the Aspen HYSYS, and you can set the color scheme for that particular variable. Now you click on cancel. And because we are doing it for temperature, so we will select simply the temperature as the variable. Now you can vary the number of segments as well over here. If I want to show only 3 to 4 colors only, I can make it to 3 colors, 4 colors, 2 colors, or maximum I can go up to 7. If you click on this auto set data ranges, it will auto set the ranges based on the. So what it will do, if you click on this auto set ranges, it will just take the data from your flow sheet, like what are the different temperature ranges or different temperature values that are there into the flow sheet, and based on that automatically it will just set the data range value. But for our particular case, I want only 5 segments, so I will just keep the 5 segments. And what are the segments like this? This temperature ranges will be like less than 128 Fahrenheit, between 128 to 157 Fahrenheit, 157 to 185, 185 to 213, and more than 213. Again, you can change these colors as well as per your likes or as per the demand from the customer. Like suppose I want this the feed line or the process lines which are having the temperature between 185 to 213, that has to be shown with red color. So you can change this according to your perception or the any demand which is coming from the customer. So we will not be changing the color scheme now. Less than 128, we will be showing it by dark blue color. So we will enter the value as 128. Now this is the value. Sorry, it has not taken that value. Enter. Let me delete this scheme and sorry, I've deleted the scheme for this temperature, I think. Okay. Value of 128 Fahrenheit. Let's start it from the top. 213 Fahrenheit. Then the next value is 185 Fahrenheit. Then the next value is 157 Fahrenheit. And next, the last value is 120. So what I've done, why I've given these four values, because what are the ranges that I am looking for is, let me explain this a little better. Suppose I'm looking for 1, 2, 3, 4, 5 ranges. 1, 2, 3, 4, and 5 temperature ranges. So the first one is less than 128. The second one is between 128 to 157. The third one is between 157 to 185. The fourth one is between 185 to 213. And last one is more than 213. That's why I have given the, you can see that here, though I have given the 5 segments, it has given asked me to enter the values in 4 ranges only. The first value is 128, I have entered. The second value is 157, I have entered. So it has understood that the second segment is between 128 to 157. So that's why I have entered this value of 157 over here. The third value I have entered as 185. So it has understood that my third segment is between 157 to 185. Then the next value I have entered as 213. So it has understood that the next segment is between 185 to 213. And by default, the last segment it has taken as more than 213. That's why we have entered such values over here. Even though we have 5 segments, you can see that we have entered only 4 values. Now I'll close this and you will see that our entire flow sheet is arranged in such a way that whatever the temperature for that particular line is there, that is represented by that particular color only. And you will understand, or you will just observe one thing, that the energy values or the heat flow values, it will be shown in some default color of gray. You will see that for this pump also it is gray, for this cooler also it is gray. If we would have added a heater over here, it would have been shown in that gray color only. Now I want this table to be displayed over here. So for that, what I need to do is I just need to check on this checkbox of display legend. And you will see that my temperature table will be displayed over here, which contains the temperature ranges and the default color, which is shown to that particular line. Now you will see that this yellow color represents the temperature between 185 to 213. Now let's open this line and check whether it is giving the correct value. Yes, for this the temperature is 200 Fahrenheit. So it is giving the correct value. Let's check for one more. This red color is having the temperature more than 213 Fahrenheit. So let's check for this line. It is 247 Fahrenheit. So it has given the correct temperature assignment for this. Let's check for this green one. It is 157 to 185. Let's check for this. This is 166. That falls between 157 to 185. So the color coding which we have suggested for this is very perfectly applied for this flow sheet. And by this we can say that we can see the different lines in different color ranges based on that temperature range which is assigned to that particular color range. I hope you have clear how to get this different lines with different who are having the different temperatures and are shown in different colors. You are clear with this? How to add this conditional formatting for temperature? You can similarly you can add this for any of the flow rate, any of the pressure range. That thing also you can. We will just try to add it for a pressure range. Suppose like add new pressure, and we will give we will keep this pressure range only, like auto set the we will click on auto set the pressure ranges and we'll click on OK. Now you will see that this has arranged itself in such a way that these pressure ranges are particularly shown by these colors. I hope it is clear to you, or no doubts in this. If you have any doubt or if this is not understood, please let me know. I will just repeat this thing. But don't keep anything which is not understood. Okay, so you are understood with this, then only last part is remaining is the changing the symbols of the equipments. That is the last part which I was sort of covered in our today's session, how to do or how to change the symbols of equipments. So suppose if I want to change the, I will just maximize this so that it can be concentrated or it can be viewed on a particular equipment. Suppose if I want to change the symbol of this pump. So what I can do is just click on this pump, right click, change icon. You can see that there is an option called as change icon over here. Just click on that icon and you can see there are some options that are given to us. Like if you want to, this is the default icon. Either I want to show it like this, like this, like this. I can select any of the icon and you will see that my pump icon will be changed like this. You'll see that everything will remain the same. Your energy stream will be shown, your inlet outlet stream will be shown, but your symbol for that particular equipment will be changed. Similarly, if I want to change the icon for my cooler, I will just click on that cooler, right click, change icon, and if I want to show this symbol like a fan, you'll see that it will be changed to that symbol. Similarly, you can do it for the columns as well. Change icon. You want me to use this symbol, you can just see this symbol is slightly modified, or like this. You can change the symbol of any of the equipment. Like for distillation column as well, it can change the symbol. And you will see that it will be shown like a simple liquid extraction column. This is actually a symbol of liquid extraction column. Let's change it to something else. It should look more or it's like the distillation column. You'll see that streams, it may appear like detached from that column, but no, they are actually attached to that column, but it will be shown like, because it is that particular symbol which we have selected. I think I forgot to tell you one thing while doing the distillation column, just a small part, it will hardly take 2 or 3 minutes. Uh, If you are simulating a distillation column, sometimes what happens is like you need to go for checking the stages by stages arrangements, or you need to have a more detailed overview of your distillation column. Then how to get that overview? You just need to double click on that distillation column, and here you will find that there is a button called as column environment. Just click on that button. It will just open pressure versus tray position graph. Just close that, and you will see that a detailed view of your distillation column. A condenser, you will see that. You will not see this view in your normal view distillation column. The condenser is how the condenser is working, how the reflux is sent back to the column, how the reboiler is working, how the boiler and the reboiler outlet streams are sent out the column. So this is called as a column environment. By entering into the column environment, you can just have a more detailed overview of how you will see that how the reflux liquid inlet is going, what is the for that particular each and every stage, it will show you the detailed information. You will be entering into the column environment. How to go back to your flow sheet again? Then you just need to simply click on this, go to parent environment. Click on this and you will see that entire flow sheet will be there in front of you. So this was just a small part that I forgot to tell you at the time of we have taken the session on distillation column. You can enter into the column environment and you can come back to the parent environment by just simply clicking on go to parent button. I hope you are cleared with our today's flow sheet. We are almost at the end of our today's session. So I will just revise what we have seen today. So today we have covered an acid gas treatment plant, which is basically an exercise on use of different types of columns in Aspen HYSYS. So in this part, what we have studied in the first part, we have seen some theory part. Acid gas treatment plant, a process which uses acid gas treatment, which is also known as gas sweetening process. It is the process of removal of acid gases like H2S and CO2 by using a amine solution. So basically this process consists of three parts: acid gas removal, which parts consist of removing the acid gases by using a lean amine solution, which is particularly carried out into an absorption column. The second part is solvent regeneration. The solvent, which is rich in acid gases, is passed through a distillation column from where the acid gases will be removed from the top, and the amine solution, which is we will calling it as a lean amine solution, which is not containing any acid gases, is removed from the bottom. That solution can be mixed up by using water as well as amine, and it can be recycled back into the system. Now the purpose of carrying out this acid gas treatment, we have seen the four purposes: safety, environment protection, product quality, and the improved process efficiency, so that these acid gases should not cause any issues like corrosion to your system. Also, it should be having a safety concern as well as environment concern as well. Then first we have seen the how to simulate an acid gas treatment plant without any recycle. In that we have four different parts, like we have an absorber, then a wall, a separator, then a heater, and a regenerator. Then in the recycle part, what we have done is we have replaced that heater with an heat exchanger so that we can form a heat exchange network between inlet and outlet of that regenerator column. Then we have seen how we can add a makeup block followed by a cooler and a pump, and we have seen the use of a recycle operation in our today's session. Then in the last part, what we have seen is how we can change the color combinations of different streams based on the temperature ranges. We have seen for temperature ranges as well as pressure ranges. Like that, you can change the different streams colors based on any particular parameter which is selected, and you can allot the ranges for that particular color of that line, and you can change it accordingly. Then we have seen one part, that is the column environment, how we can check the details inside the column by going into the column environment, and we can return back by simply clicking on the button, go to parent. So this was all about the today's session, that is on acid gas treatment plant. There was one unanswered question from my end. I thought of clearing it today, but because of time constraint, we will be covering that question or the doubt in the tomorrow's session. The question was about when the pressure and when the flow specification has to be given for a liquid product in terms of a total condenser. So I will be like clearing that doubt into the tomorrow's session. So let's stop for this today's session, and tomorrow session will be from 3 p.m. to 5 p.m. and it will be on NGL fractionation. So thank you. Thank you for attending the today's session. Tomorrow for the session on NGL fractionation.